go into the terminal and activate the environment. Right now, Jupyter Notebook. And so this is the custom metric thing, right? Yesterday, Seshiram asked how to do recall and precision. So I am using precision and recall, right? So how this worked? There are two ways of doing it. One, see this here, I changed the target variable into one hot encoding, two categorical. Okay, so this way, for every record, there will be 10 values, 10 numbers. Okay, zeros in the place where the record doesn't belong, and one in the place where the record belongs. If the record belongs to 6, right, at 6th place you will have 1, rest all are going to be 0. Right? That's how it is. For every record, there is going to be 10 numbers. Okay, and then when we are using the precision and recall, it is actually expecting 10 numbers in the actual y, the original y, and anyway we will get 10 numbers in the prediction. So let me try to comment these two, uncomment those two, and then try to execute. You will see error. So this part, right? This part I tried implementing, but it was taking too much time. So we will implement this later. Okay, this is needed, right? Custom cast functions are needed. See that we are getting error. Okay, when I kept the y variable as it is, right? In this you will have only one number in the target variable, right? For every record, there is going to be one number. If you look at the error, see that shape 1 comma none and none comma 10 is incompatible. Why that is said like 1 comma none comma 1? Because a one dimensional array are see, one dimensional, it's a kind of vector, right? So vector will have one column there, right? So y value has got only one column, but the neural network, the outcome is actually giving 10 numbers. And the cast function, right, this precision is trying to calculate on a multi-class classification. How precision is calculated, do you remember? I'm actually struggling to explain, but do you remember how precision is calculated on a multi-class classification or recall or confusion matrix? Do you remember? If you remember that, right, why this error is coming, we'll be able to understand easily. Anybody? How is the precision is calculated or recall is calculated on a multi-class classification? See this? Do you remember this diagram?
It's a kind of heat map.
Yeah, right, kind of heat map. But the way it is calculating the precision recall is for every class it will calculate precision. Right? For every class it will take the in this confusion matrix, right? For this particular class, these are the false negatives, these are the false positives, these are the true negatives, this is the true positive here, right? So
If I have to calculate precision for that particular class, true positive divided by true negative plus true positive, right?
So this number, sorry, so true positive plus false positive, right? This number divided by these all counts, right? This number divided by these all counts is the precision, right? For this particular class, that's the precision. For this particular class, the recall is going to be TP divided by this all count, the sum of all these counts. Agreed? Agreed, yes, no?
Yes, sir.
Yes, sir.
So that way, right, you will have precision for all the classes. Recall for all the classes. If you have 10 classes in your data set, you will have 10 precisions and 10 recalls. How do you calculate one number and show? If you see this here, if I say precision, I am getting one number. How do you do that? Micro, macro and weighted averages of the precision recalls I explained that day, right? So if you take micro, right, it's going to be average of all the, all the precisions, right? Macro is going to be, I forgot, macro and micro. One is average, the other one is um, uh, I forgot. So weighted is actually going to give weightage to the number based on number of records. It will give weightage to the precisions and recall scores, and then ultimately it will calculate the final score. So you look at the API, you will know what is micro, macro, and weighted averages. So basically, even in deep learning, right? When I say precision on a multi-class classification, it need to calculate the that micro, macro stuff, right? So to do that, it needs this kind of confusion matrix. To create that kind of confusion matrix, it needs in the input data, right? For every y variable, there should be 10 numbers, and we are predicting 10 numbers. Using this and that, it will calculate the total matrix, and using that, it will do whatever, right? So the bottom line is y variable should also have 10 numbers, as we are getting 10 numbers out of this network. So that's what I did here. So I commented these two, right, and then uncommented this, right. This one is like y variable is transformed into a categorical, sorry, one hot representation, and now it will work. Now precision recall methods will work. Okay, if you don't want to do that, right, you can actually predict here and then calculate all different classes precisions and recalls or confusion matrix, and then do all that, do the um, total micro, macro and weighted total formulas you can write here. Okay, so now it's working. So we have got precision 95, recall 93. On test set 95, 94. So the prediction, right? On the test set, I made predictions, and I have got for each record, I have got 10 numbers, right? And I took the argmax of the 10 numbers, so I got prediction here. Okay. So y test is like this. So I need to take argmax here also, because if I take argmax, right, the first record will be 8, second record will be 1, third record will be 9. So this is argmax, and again argmax, and then I got the accuracy score 95%. This leave it. I was actually experimenting some things there. I'll show you. We actually have to learn some basics about TensorFlow. I did not explain them. I'll explain them when we play with dataset. Got it? Precision recall we can find, right? This file is already uploaded. Okay, any questions?
Sir, what is this data set, sir? I missed a few minutes in the study.
Same dataset. I did not change dataset. I'll change dataset in CNN only. CNN Now we'll do cat dog classification.
So the output is actually having the 10 distinct values, right?
Ah,
So again, why we made it a kind of one hot encoding?
that's the reason I explained here. So precision and recall, these classes, right? They're expecting 10 values out there to calculate the the precision recalls for each class. I know maybe I should implement that and show, but maybe I'll do that later. So your question, right? Your question is like, if I have a target variable only one value, what will happen, right?
Yeah.
So here the implementation inside this precision class is in such a way that maybe I should explain that in a different way. Let me try to. So if I have to write precision class here, if I have to implement precision class, I'll implement it like this. Let me try to take a. So then you will understand. It is all how the internals are working. If I have to implement that precision class, right? What I will do is, suppose that there is a record. Y. I think I should reduce the size of this. Y1. Okay. First record. Okay. First row's y value. I suppose that is 8. Okay. And y1 cap. This is predicted value, right? So I have got an array, right? 0.02, 0.05, and so on. At 8th place 0.9, and on the 9th place 0. Maybe 0.7, something like that. Okay. So these are the 10 probabilities. Now I have to, now if I have to calculate precision, I actually explained, but if I have to calculate precision, what I should do? I should calculate precision for class 0, precision for class 1, precision for class 2, and so on, precision for class 9 I need to calculate. Total precision P is equal to P0 plus P1 plus and so on, P9 divided by 10. That's the ultimate precision. No, macro precision. Okay. So to do this P1, right, what we should do? What is P1? Sorry, P0. P0 is, right, P0 is this number divided by the whole total of this, right? So sorry, this number divided by the total of this. So at 0th class, how many are correctly predicted? Divided by maybe 8th class. Maybe we'll take 8 here. P8. Right? So uh, so every record will not belong to 8, right? Every record will not belong to 8. So when the record is not belonging to 8, does it predicted as 8 or not? That also we have to see. So here I am actually struggling. We can do one thing here. If I represent this as one heart, right, what happens? 0, 0, and so on, 1, 0. If I multiply these two, right, y1 and y1 cap, y1 cap. If I multiply these two and add, right, sigma I is equal to 1 to k, right, k classes, multiply them and add them, what I'll get? 0.9, right, 0.9. So if this is greater than 0.5, right? This is greater than 0.5, greater than or equal to, that means the prediction is 1, right? That means 8, right? So this is so to find this out, right? Give me one second. To find this number or this number, what we need to do is how many total 8s are there in a target variable. We need to see how many total 8s are there. Total 8s in the data set, and then we need to see how many 8s are predicted as not 8, right? P now 8 as not 8 and P 8 as 8, right? So if I know these two counts, right? If I know these 3 counts, then I'll be able to calculate precision for 8. Okay. So if I take this 1-hot encoding representation, right, inside the precision class, it is doing something like this. It is multiplying all these numbers and summing, and then applying threshold to find out all 8s predicted as 8. Got it? Sisramgar.
Yes, sir. Yes.
Right now it need to find out how many 8s are there in the data set. That can be done using this y cap, right? Y1 where that is equal to 8, that actually gives the shape, whatever that array's shape will actually give the count how many 8s are there in the data set, right? How many are predicted correctly, this is. How many wrongly predicted is going to be this minus that, right? So 3 numbers are there, you can actually calculate precision. So if you have 1-hot representation, right, it is easy, right? If it is not 1-hot representation, right, what we should do is, if it is not 1-hot representation, we can do that also. If it is not 1-hot representation, but this is how the calculation is happening inside the TensorFlow, right? Whatever. So I tried to implement this yesterday, but it was taking too much time, so I stopped doing it, and then came back to whatever this 1-hot representation. I'll do that, maybe in coming classes and explain. So if 1-hot representation is not there, what we should do is, this 1 is 8, right? And then y1 cap is actually like that array, right? 0.02, 0.05, and so on, 0.9 and 0.07. We have to take argmax of it. Argmax in NumPy also we have, TensorFlow also argmax is there. Okay, argmax of that is going to be 8, right? So like this we need to calculate. We need to find out all the 8s in the data set by filtering the data and finding out the shape. And then how many 8s are predicted as 8, we need to actually see. We need to take all those records, y values, and then we need to do argmax and see how many equal, right? Again take the count, right? Like that we need to. So implementation will change. We can actually implement this or that, but internally the guys who implemented precision class actually took the same dimensional vectors to calculate the true positives, false negatives, and all that stuff. Got it? That vaguely I explained, but I'll write some code here, and we can use these also. Okay. So these are not working. This is not working now, but we need to do our own implementation. So we can actually use these directly here, but not inside the method. I tried to do some experimentation to calculate F1 score, but couldn't do it. We'll do that. Okay. Got it?
Yes, yes, sir.
This is where you need to play with TensorFlow a little bit, right? So those questions, it takes time, but when you experiment, right, you get a lot of confidence, and these are the things we have to do in the real time. Okay. So coming to the hyperparameter tuning, Girigar was asking this for a long time. So, first there are many hyperparameters in deep learning, right? Deep neural network. With CNN, right, we'll have more, right? So there are hyperparameters like number of layers, number of units, learning rate, learning schedule, betas, epsilon, L1, L2, dropout. All these are different parameters. So we should actually play with learning rate first and see how in how many less iterations the model is actually converging or converging faster convergence we have to see, and then we should increase or decrease hidden units, right? First we should start with a small neural network and play with the learning rate and make the model work, then increase hidden units and see whether it's overfitting or not, right? And then maybe with one layer, one hidden layer, we'll increase the hidden units and see how the model is working. Then mini batch size. Sometimes what happens is, if your mini batch size is too small, algorithm will struggle in learning. Why? Algorithm will struggle to learn the pattern when the mini batch size is small. Why? How does mini batch size affect the model learning behavior?
If the number of records are less, then the generalization is less, right?
Generalization is less and oscillation is going to be more. In the W's, weights, oscillation is going to be more, and it may get distracted. Your model is going in a right direction for 10 iterations. Maybe from 11th to 12th, 11th to 13th, it actually deviated, and again the weights need to get adjusted. So it's like going backward and forward, right? If you increase batch size, the generalization is going to be more, and the learning is going to be in a proper direction. Why not take all data? Why need to take batch, mini batch? Why not take all data at once? That will generalize better, right?
Yeah, it's the hardware.
Hardware, memory is not sufficient, right? Generally, right, the artificial intelligence is getting popular because of the way it can play with the unstructured data and bring insights from it. Unstructured data is in huge volumes in the industry, so you should have a way to process data, in batches only. That way you can handle huge volumes of data, petabytes of data, zettabytes of data. No struggle. It may take time, maybe a month, but ultimately it will learn, right? So that's mini batch. Okay. So mini batch size you need to play with to make the model learn better. When it is learning better, overfitting will reduce. Or sometimes bias will also may come in, but generally overfitting will happen when batch sizes are small. Okay. And then betas, right? Those in the advanced optimization functions like momentum and RMS prop and Adam, the betas are there, right? You need to play with them, but generally you will not play with them, right? Number of layers then. Okay. So hidden units we played, now mini batch size we played, still we did not see much improvement. Now increase the number of layers. So you shouldn't be starting a neural network with 100 layers. You should start with 1 or 2 layers and see how it's working. Then you need to increase the layers, right? So units you can actually play with also. In one layer more units, one layer less unit. That also you can play with. Okay. And then learning rate decay and other hyperparameters. Other hyperparameters are like I think dropout and all these regularization hyperparameters are there, right? L1, L2 dropout and all. You can play with them. Okay, that's how it's that's the order in which you need to play with the hyperparameters. Is there a simpler way? I think we have seen, right, that grid set CV approach, right? So it is working. So you can use that, but when you use grid search CV, it takes a lot of time, right? You need to do cross validation and all that, right? So with different hyperparameters. Yeah, we have that automated approach. Okay. So with this, right, I'll say the DNN is done. Any questions in DNN?
Sir, here hidden units is nothing but the number of neurons in a hidden layer.
Avunandi. Yes, hidden units means nodes in the hidden layer. Neurons in the hidden layer. Okay. So let's jump into the CNN. Right. Okay. So convolutional neural networks. In DNN, right, there is one problem. When we looked into the weight matrices and the manipulation, right, theta transpose X. Suppose there are 400 by 400 by 3. So yeah, so if there is a picture, right, there is a photo with 400 by 400 by 3 dimensions, right? What is 400 by 400 by 3? In a picture, there will be in a color picture, there will be 3 channels, okay? Red, green and blue, RGB, right? Suppose that the dimensionality is 400 by 3. How many pixels are there in that picture? 400 by 400 by 3 picture. How many pixels?
64,000.
I think 48, sir.
16,000.
1600 into, yeah, 1600, right? 16,000 into 3, yes, sir.
48,000.
48,000, right? Now, if you are trying to build a neural network, right? So let me take a new document there. So there is a picture with 400 by 400 by 3. That means there are 48,000 pixels, right? Okay, there are 48,000 pixels. So now I wanted to classify whether this picture is a dog or cat. Suppose that, okay? So to do that, what I can do? I can do a deep neural network, right? DNN. So the x's are going to be like this: x1, x2, and so on. X 48,000. Okay. And suppose that I have taken 100 neurons. 100. Right. So one layer. Let us look at one layer. So now, what is the weight matrix size here? Weight matrix size. If bias term is not there, suppose that bias term is not there. Don't be worried about bias term. What is the weight size? Weight matrix size?
48,000 into
1 by 48,000.
Yeah. So you know, for each node you need 48,000 weights, right? That's a vector, right?
Yeah.
48,000 W1, W2, and so on. W 48,000. Right? So like this, right? For 100 nodes, you need 100 rows, 100 columns. Right? 48,000 by 100. So I am actually reiterating this thing many times because it actually give, you will remember. Okay. So it's going to be 48,000 by 100. How many numbers it is? 48, 3 zeros, 2 zeros, right? So you know each is a float 32. Suppose that each cell in this matrix is a float 32. Right? 32 bit. 32 bit into 32, right? Into 32. Let's see how much that number is.
Sir, 1 second.
Sorry?
That 100, can you tell me what is that 100, sir? I missed
Yeah,
that.
that's a good question. No, basically we get confused. Let me try to draw again, okay? Basically, I used to get confused. The matrix size, right? I used to get confused. Okay, so I cannot wipe this out. Give me 1 second. These tools, right? Junk. Yeah. See that? I need to fill with white, I think. Okay, let me explain here itself. So for this first node, oh my god. For this first node, right? What happened? For this first node, how many weights we need? 48,000, right? That point is clear?
Yes, sir.
Right? For the second node?
Yes, same thing.
Right?
Yeah.
Like that, I have taken 100 nodes here.
Okay. 100 is the number of nodes. Okay.
Number of nodes. So there will be 100 columns.
In that layer, there are 100 nodes. Sir.
The weight matrix size I am actually trying to. These arrows, right? How many arrows are there? Each arrow is a number. Right? This number is one arrow, this number is another arrow, this number is another arrow, like that. Right? Got it?
Yes, sir.
And each number is at float 32. So it's going to be, right? There are 48, no one. So 48, 48 lakhs, 4.8 million, 4.8 million weights they are, right? Into 32 bits, right? The total 48, 5 zeros into 32, right? That many bits it is, divided by 1024 is the kilobytes, right? Divided by 1024 megabytes, right? 146 MB it is going to take in one layer. Okay, suppose that my batch size is 32, right? Here I took only one record, but if the batch size is 32, what will happen? The batch size is 32, what will happen? For each record, it is going to take that matrix and multiply, right? This 146 or 147 MB matrix is going to multiply this 48,000 matrix, right? And you get the 100 nodes as output, right? So this is this is actually occupying lots of space, and in text problems, right? We have seen in that bag of words representation and the TF-IDF representation. Did we get thousands of columns there? Did we get thousands of columns there?
Yeah.
Even there also, if you use deep learning, deep neural network, it will occupy too much space. It will occupy too much memory, right? Memory requirement is going to be high, and there is going to be many batches and many layers and many iterations, right? The memory is not going to get cleared in fraction of seconds. You know that, right? In Java, if memory need to be get clear, right, it takes time, and we cannot force it to remove. And there is a concept called as I forgot that.
Garbage collector.
Garbage collector, right? It works at its own will, right? There is no control over it, right? Garbage collector will take care of cleaning it. Even Python is based on that kind of concept only, right? So, and the other thing is this whole memory is occupied in the GPU, in the GPU RAM, not in the RAM we have. So in GPU, right, you will have maybe 8 GB or 10 GB, 8 GB or 12 GB, or maybe 16 GB, right? So if you want to build a neural network for these kinds of data sets, whether it is text or images, deep learning is not suitable. That's where we are actually going into convolutional neural network, right? DNN will not be able to scale to handle these kinds of huge feature data sets. So CNN can solve that problem. One problem that CNN can solve is this one. The second thing is, in a picture, right? If you look at this picture, suppose that this is a picture, okay? Don't look at numbers, only look at the shades, right? Gray shade and white shade. Give me 1 second. See, if you look at that gray shade and white shade, right? CNN, right? As a human being, we are actually able to understand that this is white shade and this is gray shade because colors have changed, right? But for a computer, right, we need to let it understand where exactly the color change is happening, right? So if you look at this, right, this is the original picture. When I apply CNN, right, this picture or this pixels will change like this. Right? This is the picture. When I applied the CNN, the picture changed like this. So it is, in this picture, this area is of one color and this area is of another color. When I applied convolutional neural network, it actually produced another matrix where you have one color in the middle and different color on the edges. Okay, that means it is actually trying to let you know where exactly the color is changing. It is, the CNN will try to highlight the edges or the places where the color is changing. Got it? That way you can actually, it is like if you ask a painter to paint your picture, right, or draw your picture, they'll just outline, right, like this. If I'm not a good artist, but somebody is doing the drawings, right, they'll actually highlight like that, right? Right? Only the lines they are drawing, but still it actually shows, it actually appears like Chiranjeevi or Balkrishna or whatever, right? So that edges are identified that actually can distinguish between different objects and different people. So basically, why we are struggling this much, we're actually trying to give some human-like capabilities to computer, right? So the CNN is efficient in identifying the edges. Edge detection is the another capability of CNN. Got it? Got it? Why we are moving into another neural network? As we already know, the deep neural network can handle huge volumes of data and it can actually, work with images or whatever, right? So we are going into this because of these are two, not all the, it is not covering all the reasons, but major important reasons I found. Okay. So let us look at some theory and then start for questions. That convolution, what is convolution? Is an element-wise multiplication, right? Element-wise multiplication, right? So if you take a 3 by 3 matrix and you take another 3 by 3 matrix, you do element-wise multiplication. You can do element-wise multiplication, right? So let me try to show that slide, maybe basic linear algebra. Yeah, this element wise multiplication, this is okay. So I have taken 10 and trying to multiply this, and I have taken two matrices here, 2 by 2 matrix and 2 by 2 matrix. When I do element wise multiplication, I am doing this multiplication. But if it is a matrix multiplication, right, that's going to be different. I think I showed a diagram, and yeah, this one, right? This is matrix multiplication. This row multiplies this column, this row multiplies this column, this row multiplies this column. And every time that we are going to sum it. This is actual matrix multiplication. This is element wise multiplication. Okay. So element wise multiplication is called as convolution. Okay. Element wise multiplication of two matrices which produce new matrix is called as convolution. The matrices derived after element wise multiplication is called as convolution features or activation map or feature map, right? In the articles, right, they write these. Surfing through internet and trying to find some things is always good, especially in deep learning, because deep learning is still evolving, and maybe for next 2 years we'll have the same situation. And frankly speaking, right, AI is still not stabilized, and it will stabilize in near future when we get a more labeled data and more trained models. Okay, we will definitely get, because lots of work is happening in labeling the data and in creating data, in creating databases that are useful in building AI models. So far the databases are built to produce reports or do some calculations only. But for AI, the data set should have labeled data. By now you would have understood what is labeled data, right? Any questions on that statement? We need labeled data to make AI work, right? Applications should be designed in a way that the store data that's going to be useful for the AI training. That is already happening. So maybe in 5 to 10 years, right, you will have all database designs supporting the data that is needed for AI training. Along with that, you will have trained models. Right? With that, right, AI will mature. Now it is not fully mature. And why am I saying this is, if you take some text problems, we cannot provide solutions, but still we use them, because it can actually solve up to 70 to 80% of the problem. Okay. So if we have that understanding that there are some capabilities, there are some limitations, we can set the expectations to the client. And I told you, right, most recently I was working with one of the client, and the team who were representing, I don't know whether they gave right perspective on how much we can solve the problem. They are struggling. So I'm kind of temporarily out of it. I'm just wait and watch kind of situation I've taken. I kind of proposed solutions, but they didn't like it. They want to suffer, so let them suffer and come back. So I kind of stand by now. Okay, so I'll show you all those capabilities and limitations here. So convolution, right? The basically these words I got from internet, where people are using. When you see convolution features, right, you may get confused. It is nothing but the outcome of the convolution. What is the outcome? Now this concept is edge detection. I said this filter is called as edge filter. The one which the one matrix that actually does the convolution is called as filter. In a way, these are weights. in a way, or frankly speaking, these are weights, right? This is W1, this is W2, this is W3, W4, W5, W6, W7, W8, W9. Okay, 9 weights they are. You can actually represent this as a vector or a matrix, but in convolution, you represent that as a matrix. In deep neural network, you represent the same weight vector as matrix. This is a very important point. Remember, okay? A weight vector matrix, a weight, the weights of a neural network. In deep neural network, we represent that as a vector. In convolutional neural network, the same weights are represented as a matrix. There is a reason. I'll explain why it is. Okay. So this weight matrix is going to multiply. There are it's a 3 by 3 matrix, right? So it's going to multiply 3 by 3 area and sum all of that multiplication. So 1 will multiply 10, 0 will multiply 10, minus 1 will multiply 10, and then sum all of it. And then it slides and comes to this area and multiplies again and sums. Like that, it is going to do edge detection, right? It's a vertical edge detection filter. The researchers found that when you apply this, if there is any vertical edge, what is vertical edge? The color is changing from white to gray. This is vertical edge. When you do convolution, right, it will find out that vertical edge. Let us see how it does. See that I applied the filter here. The outcome is like this, right? 1 10 multiplied 0 10 10 minus 1, right? All these multiplications, right? And then summed all of it and putting it in here in a cell, and then it slided a one column and then multiplied and kept here. Another column multiplied, right? Like that. It is going to, right? It's going to, when in the next step, right? It's going to come here and multiply and then put the value here. Slide it, multiply, put the value here. Slide it, multiply, put the value here. Like that it's going to do. Okay. So once after doing all that, right? The original matrix is 6 by 6 matrix. We have got a 4 by 4 matrix. But here you see the color actually, the highlighted area became the middle part. So there is a edge, right? If all are 10, right, you would have got all 30s here. Even here also, if you had 10s, you would have got all 30s in total matrix. That means there is no edge. If there is edge, right, there is difference in the numbers there. Got it? That is edge detection. Basically, convolutional neural network works like that.
So one question, sir.
Sorry?
One question, sir.
Yes.
We chose 3 by 3 matrix for the multiplication. So I think what to choose also, I think it matters, right?
Yeah, that's a hyperparameter. And the size of the filter, right? Number of weights is the size of the filter. Here I took number of weights 9. Okay. Size of the filter became 3 by 3. So in convolution, right, we always talk in terms of 2-dimensional, 3-dimensional matrices as weights. Because we are applying, it's a element wise multiplication rather than, it's a linear combination only. But in DNN, right, it's a 6 by 6 matrix. That means 36 inputs. X1, X2, X3, X4, X5, X like that, right? Like that, right? And these are all X1, X2, X3, X4, and so on, X36 pixels. Okay. The W1, W2, W3, and so on, W9 only. But in deep neural network, we used to take 36 weights. For 36 x's, we used to take 36 weights. But in convolution, we are not going to do that. It's a little intelligent way of handling huge volumes of, where the number of columns are more. We'll see the advantage in coming classes, but high level I am trying to show the difference. Got it?
Okay. So just an example, we can take we took here in this example 3 by 3. We can take 2 by 2 also if you want. Isn't correct, sir?
2 by 2 also we can take.
Okay, sure.
We can take 1 also. 1 by 1 also.
Sure.
But generally we choose odd number. There is a reason, right? When the reason is like when you applied the filter, right, the dimensionality is reducing. So while the dimensionality is reducing, there is a calculation there. The odd number actually helps. I'll show that also. We have formulas and all. Simple formula.
Sure.
Any questions?
So the filter matrix will be always m by m.
Yes, and it's a square matrix only.
Yes.
Even if there are extra pixels, right, we'll ignore them. We'll make it a square matrix. Okay. So there are different filters already found by the researchers. Right? This is horizontal filter. If there is any horizontal line or the deviation in color, this will try to distinguish as it does the vertical one. It's Sauber and Scar. I forgot. There is some theory behind it. I forgot it, but no need. So. So the point I was trying to highlight here is edge detection is very important, right? When I showed you this picture, right, there is a here it is vertical edge, but if you come down a little bit, right, it's a little bit slant edge. Again another slant edge. And these are all small edge lines which actually join together, right? So to find out exact pattern in this picture, we may have to use many filters. Right? Maybe a vertical edge may find out, vertical edge filter may find out this edge and this edge, and maybe in some places maybe this edge, like that. But there are edges which are belonging to 45 degrees, 30 degrees and all, right? You need to have different edges to find the pattern inside the pattern inside the picture, right? So to do that, I said these are like weights, right? So if a neural network can learn those edges, right, those filters, right? This one filter is found by researcher, this one filter found by researcher, but if you build a neural network, if that can learn those weights, right? One filter will learn vertical edge, another filter will learn horizontal edge, another filter may be 40 degrees edge, another filter may be 58.5 degrees edge, depending on the data. If the filters are learning or these numbers are changing, initially they are random numbers, right? Over a period of time, when you do network for a certain amount of time, these weights will get adjusted. Let me show you one network. See this here, this is a convolutional neural network. There is a picture 39 by 39 by 3. I have taken 30, I have taken the 3 by 3 filters, 10 filters I have taken. Right here, it's a 3 by 3 filter, one filter. Right here it is one filter, right? Instead of taking one filter, I have taken 10 filters there. Okay, and in the next layer, I have taken 5 by 5 filters 20. In the next layer, 5 by 5 filters 40. Right? Like that, I applied. While applying, right, I actually took the target variable into consideration, right? Y variable into consideration. So I have chosen all the random weights in the filters, and I was actually multiplying, reducing, multiplying, reducing, multiplying, reducing, and trying to predict. When I am multiplying, reducing, and trying to predict, right, these weights will get adjusted in such a way that the y variable, y cap is produced close to y. Right? In that way, right, these filters are learned filters. They are all dynamically learned filters. Rather than me specifying the numbers inside the filter, those random numbers get adjusted. That's the neural network there. Got it? Convolutional neural network. The point is, a filter can identify edge. A filter can identify edge. That is this example, right? But a static filter, like a vertical or horizontal filter, is not of much use. But is there a way that a neural network can learn the filter so that it can identify different edges in a picture, right? one picture and other picture will differ in the way the edges are present, right? My face and other person's face will have difference because the edges are different, the shape is different, right? So that the differences in shapes can be identified or can be captured by the filter, this filter, right? But this is a static filter. It can identify only vertical edge. But in a neural network, right, you can make you can randomly choose filters, 10 filters here, 20 filters here, 40 filters here. That means around 70 filters we have chosen. Those all filters are random numbers initially. Using gradient descent, they get adjusted in such a way that the target variable differences will be identified. When you are classifying a record, that means you are actually identifying the pattern differences in target variable, right? Or the relationship between the input and output, right? Got it? Got it? Any questions? No? Is it clear? Confused? Clear, right? Can I move on? Nobody is talking.
Yes.
Not understood, huh?
Okay.
Getting it, eh?
And maybe once we keep seeing more and more, we have.
Yes, and yes, definitely, sir.
Just
But
only
you should think along, right? This is a black box, right? I'll try to demystify, right? I think deep DNN is clear now, right? Is it? Is it clear now? Maybe I'm assuming.
Yeah, DNN is a little better than this.
Yeah. So this will also get clear, in next 2 days, right? You'll know a lot of things about CNN, and very exciting. I kind of wait to come and explain these or work on these kinds of projects. Basically, it's very exciting. I'll show you all that. What is there in this, right? Basic idea is that. Basic idea is filters can identify edges, and we are learning filters in the neural network. In deep neural network or a machine learning algorithm, we are learning weights. Here also we are learning weights only in a systematic way, in a matrix format, right? We call those matrix formatted whatever weight things are called. We call them as filters. Okay, so I'll stop here and start tomorrow because a little gap is needed. You need to think a little. You need to have some kind of a space to think a little bit. Have a bit of thought running in your mind, and we'll see all image processing and all. A little bit of image processing we'll see first, and maybe we'll cover object detection also, and then go into NLP. That is better, I think. Okay. Yeah, we'll cover object detection also, and then we'll go into NLP. We can do exercise on object detection. That's a very exciting thing. In Collab itself we can do. Okay. So,
Yeah. So.
yeah.
No, don't stop.